Assalamualaikum warahmatullahi wabarakatuh. So this is the fourth topic in our syllabus HE035, which is the acid-base equilibria. If you look at to the textbook, this is under the chapter 18 of our textbook. So under this topic, there are several subtopics that we'll cover. Of course, that will start with the theories of the acid and base, when you have to be able to define acid and base from several scientists. Then we look at the properties of the salts that is produced from the reaction between acid and base. Then we look at the buffer system and also the common ion effect. And lastly, we look at the titration for the reaction between acid and base. Have to be able to calculate the pH during a reaction. The pH of the strong acid, strong base, weak acid, weak base. The pH of the salt, the pH of the buffer solution. And for the titration, we have to be able to calculate the pH at the initial point, a point before the equivalent, a point at the equivalent, and a point after the equivalent. Okay, so these are examples of the acid and base that we can find in our daily life. This is from table 18.1 in our textbook. Okay, if you look at the acid, we have acetic acid that is used as flavoring and preservative. We have citric acid, phosphoric acid, boric acid. Okay, boric acid, it can be used as antiseptic. It is also used as the food preservative. We have aluminium salt, HCl, and so on. Okay, example of the base that we use in our daily life is the sodium hydroxide, ammonia, sodium carbonate, and etc. So let's look at the definition of acid and base. Okay, when we look at the Arrhenius, it defines acid and base based on the ability of the substance to produce H plus and also OH minus when they are dissociated in water. However, the Lewis defines acid and base based on the substance that donate electron pair or the substance that accept electron pair. And lastly, Bronsted-Lowry define acid and base based on the proton transfer. It is based on the proton donor and the proton accepted. So we are focusing on the Bronsted-Lowry theory when we identify the acid and base. So according to the Bronsted-Lowry, the acid is a substance that donate a proton to another substance. Proton in this case is H plus. However, base is a substance that accept H plus or proton from another substance. Okay, so the proton donor is an acid, while proton acceptor is a base, according to the Bronsted-Lowry. So let's look at this example. How can we identify which one is the acid and base according to the Bronsted-Lowry? We have a reaction between HCl and H2O, and it produces chloride ion Cl minus and H3O plus. Okay, so from this reaction, we can see that HCl turns to Cl minus during this reaction. So what happened to the HCl? HCl is actually donated its H plus or its proton to the H2O. Okay, while H2O receive H plus or proton from HCl. So since that HCl is the proton donor, so HCl is an acid, while H2O is the one that receives H plus or proton, so it is a base. Another example, when we have a reaction between ammonia and H2O, it produces ammonium ion and hydroxide ion. If you look at this, ammonia turns to ammonium. What happened to the ammonia until it turns to ammonium? So H2O donate H plus to the ammonia, so that ammonia turns to the ammonium, and ammonia receive H plus from H2O. So ammonia is a proton acceptor, H2O is the proton donor. So ammonia is a base while H2O is an acid according to the Bronsted-Lowry definition. So the extension of the Bronsted-Lowry definition, okay, makes us to have a conjugate acid and also conjugate base. So the conjugate acid is actually the resulting species when a base accepted H+, while conjugate base is the resulting species when an acid lost H+. Okay, let's consider this reaction. H2S plus NH3 produce HS minus and ammonium ion. Okay, so this is a reversible reaction because we look at to this reversible arrow. So if we consider the forward reaction, okay, what happened is the ammonia accept H plus and H3 accept H plus from H2S and ammonia form ammonium. While H2S donates its H plus to ammonia and H2S turns to HS minus. Then if we consider the reverse reaction of the same equation, okay, it is when ammonium is the one that donates its H plus to HS minus. So ammonium turns to ammonia. And HS minus is the one that receives H plus from ammonium. And HS minus turns to H2S. Okay, so if we consider the forward reaction, H2S is the one that donates H plus, so H2S is an acid. Ammonia is the one that receives H plus from H2S, so ammonia is a base. As for the reverse direction, ammonium is the one that donates H plus to HS minus, so ammonium is an acid, and HS minus receive H plus, so HS minus is a base. Okay, that is why, okay, the partner will be H2S, its conjugate base will be HS minus, while ammonia is a base, its conjugate acid will be ammonium. So if we have an acid, the first acid, its pair will be base. Okay, when we have the base, its pair will be acid. Then we say that conjugate acid base pair. So a Bronsted-Lowry acid-base reaction occurs when an acid and a base react to form their conjugate base and also conjugate acid. Okay, so let's look at a basic reaction between acid and base. So when an acid is reacted with a base, they are actually producing a conjugate base and also conjugate acid. Example, we have a reaction between HF and H2O. It produces fluoride and H3O+. So during this reaction, HF donate H plus to the H2O. So HF is an acid, H2O receive H plus, so it is a base. Then F minus is the product of HF. Okay, so when this is an acid, F minus is its conjugate pair, so this is the conjugate base. Acid, the partner will be base. H2O is the one that receives H plus, so H2O is a base, so its partner will be H3O plus, so H3O plus is the conjugate acid. Reaction 2. We have a reaction between HCOOH and also Cn minus. It produces HCOO minus and HCN. So obviously that HCOOH donate H plus to the Cn minus. So this is an acid. So the partner is the HCOO minus. So this is a base, a conjugate base. Cn minus receive H plus. So Cn minus is a base. Its partner, it produce HCN, will be conjugate acid. Reaction 3. Ammonium acid, carbonate base, ammonia conjugate base, HCOO minus conjugate acid. Reaction 4. H2PO4 minus acid, OH minus base. So H2PO4 minus produce HPO4 2 minus. So this is a conjugate base. Okay. OH minus produce H2O. So this is a conjugate acid. Reaction 5. Acid, base, conjugate acid. Acid, base, conjugate acid. So if you look at to the formula, all conjugate base will have a less one H than the acid, while the conjugate acid will has more one H than the base. Okay, so if you look at to this figure 18.9, okay, these are the list, the ranking of the strength between acid, base, and their conjugate pair.